Welcome to Study Loop.
So we know we're going to need to use the parallel axis theorem. And equation 1034. So once we use this, we can use the subscript L for the long rod and the subscript S for the short rod. And we can say that for part A, the rotational inertia would be equal to the moment of inertia of the short rod plus the moment of inertia of the long rod. This would be equal to 1/12 times m sub s, the mass of the short rod, times the length of the short rod squared, plus 1/3 times the mass of the long rod times the length of the long rod squared. And solving, we find that the moment of inertia is equaling 0.019 kilograms meter squared. So this would be your answer for part A after essentially just plugging in. And then we can say that for B, we're noting that here we note that the center of the short rod is a distance h equaling 0.25 meters from the axis. So this would be center of short rod from axis. And we can say that here the rotational inertia would be I equaling I sub s plus I sub L. This would be equal to 1/12 mass of the short rod times the length of the short rod squared plus mass of the short rod times h squared plus 1/12 times the mass of the long rod times the length of the long rod squared. And plugging all of it in, this is going to equal the same exact moment of inertia, 0.019 kilogram meter squared. This would be your answer for part B. We only calculated the moment of inertia in a different way using here essentially we are using more of the parallel axis theorem, given that we're noticing that the the short rod is 0.25 meters away from the axis of rotation. So instead of using 1/3 for the long rod, 1/3 coefficient of 1/3, we use a coefficient of 1/12, and then we add the mass of the short rod times h squared. Again, either way, we're going to come to the same answer. Again, the moment of inertia, 0.019 kilogram meter squared. That is the end of the solution. Thank you for watching.